The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, good morning, everyone. Let's get started. So, we're going to start 6046 in earnest today. We're going to start with our first module on divide and conquer. You've all seen divide and conquer algorithms before. Merge sort is a classic divide and conquer algorithm. I'm going to spend just a couple of minutes talking about the paradigm, give you a slightly more general setting than merge sort, and then we'll get into two really cool divide and conquer problems in the sense that these are problems for which divide and conquer works very well, namely convex hull and median finding. So before I get started on the material, let me remind you that you should be signing up for a recitation section on Stellar, and please do that even if you don't plan on attending sections, because we need that so we can assign your problem sets to be graded. Okay? So that's our way of partitioning problem sets as well. And then the other thing is problem set 1 is going to go out today, and it's a 1-week problem set. All problem sets are going to be a week in duration. Please read these problem sets the day they come out. Spend 5-10 minutes reading them. Some things are going to look like they're magic, that they're, how could I possibly prove this? If you think about it for a bit, it'll become obvious. We promise you that. But get started early. Don't get started, at 7 p.m. when we have a 11:59 p.m. deadline on Thursday, right? That 4 hours or 5 hours of time may not be enough to go from magical to obvious. Okay? So let's get started with the paradigm associated with divide and conquer. It's just a beautiful notion that you can break up a problem into smaller parts and somehow compose the solutions to the smaller parts. And of course, the details are going to be what's important when we take a particular problem instance. But let's say we're given a problem of size n. We're going to divide it into A subproblems. I'll put that in quotes so you know it's a symbol. A subproblems of size n over b. And here, A is an integer, and A is going to be greater than or equal to 1. It could be 2, it could be 3, it could be 4. This is the generalization I alluded to. And B does not have to be 2 or even an integer, but it has to be strictly greater than 1. Otherwise, there's no notion of divide and conquer. You're not breaking things up into smaller problems. So B should be strictly greater than 1. Right? So that's the general setting. And then you solve each subproblem recursively. And the idea here is that once the subproblems become really small, they become constant size, it's relatively easy to solve them. You can just do exhaustive search. If you have 10 elements and you're doing effectively a cubic search, well, 10 cubed is 1,000. That's a constant. You're in great shape, right? As long as the constants are small enough. And so you're going to recurse until these problems get small. And then typically, this is not true for all divide and conquer approaches, but for most of them, and certainly the ones we're going to cover today, the smarts is going to be in the combination step. When you combine these problems, the solutions of these subproblems into the overall solution. And so that's the story. Typically what happens in terms of efficiency is that you can write a recurrence that's associated with this divide and conquer algorithm, and you say T of n, which is the running time for a problem of size n, is going to be A times T of n over B, and this is a recurrence, plus the work that you need to do for the merge operation, or the combine. So this is the same as merge. And so you get a recurrence, and you're not quite done yet in terms of the analysis, because once you have the recurrence, you do have to solve the recurrence. And it's usually not that hard, and certainly it's not going to be particularly difficult for the divide and conquer examples that we're going to look at least today. But we also have this theorem that's called the master theorem that is essentially something where you can fairly mechanically plug in the A's and the B's and whatever you have there, maybe it's theta n, maybe it's theta n square, and get the solution to the recurrence. I'm actually not going to do that today, but you'll hear once again about the master theorem tomorrow in section. And it's a fairly straightforward template that you can use for most of the divide and conquer examples we're going to look at in 046, with one exception that we'll look at in median finding today, that will simply give you the solution to the recurrence. Okay? So you've seen most of these things before. That's a little bit of setup. And so let's dive right into convex hull, which is my favorite problem when it comes to using divide and conquer. So convex hull, I got a little prop here, which will save me from writing on the board and hopefully be more understandable. But the idea here is that in this case, we have a two-dimensional problem with a bunch of points in a two-dimensional plane. You can certainly do convex hull for 3 dimensions, many dimensions. And convexity is something that is a fundamental notion in optimization. And maybe we'll get to that in 6046 in advanced topics, maybe not. But in the context of today's lecture, what we're interested in doing is essentially finding an envelope or a hull associated with a collection of points on a two-dimensional plane. And this hull obviously is going to be something, as you can guess, that encloses all of these points. Okay? So what I have here, if I make this string taut enough, this is not working out so well, but I think you get the picture. All right, so that's not a convex hull. Okay? This is not a convex hull for the reason that I have a bunch of points outside of the hull. All right? So let me just... That is a convex hull. Okay? And now if I start stretching like that, or like this, or like that, that's still a convex hull. Okay? So that's the game. We have to find an algorithm, and we'll look at a couple of different ones that will find all of these segments that are associated with this convex hull. Okay? So this is a segment that's part of the convex hull. That's a segment that's part of the convex hull. If, in fact, I had something like this, and this was stretched out, because I have those 2 points outside the convex hull, this may still be a segment that's part of the correct convex hull, but this one is not, right? So that's the game here is to find these segments. So we're going to be working with segments or tangents. They're going to be used synonymously. That are all of the tangents or segments associated with the entirety of the convex hull, and we have to discover them. And the only input that we have is the set of points, xi, yi coordinates. Okay? And there's just a variety of algorithms that you can use to do this. The one that I wish I had time to explain, but I'll just mention, is what's called a gift wrapping algorithm, where you might not have done this, but I guarantee you that you probably have taken a misshapen gift, right, and tried to wrap it in gift wrapping paper. And when you're doing that, you're essentially, if you're doing it right, you're essentially trying to find the convex hull of this three-dimensional structure. You're trying to tighten it up. You're trying to find the minimum amount of gift wrapping paper. I'm not sure you ever thought about minimizing gift wrap paper, but you should have. That's the convex hull of this three-dimensional shape, right? But we'll stick to 2 dimensions because we'll have to draw things on the board. So let me just spec this out a bit. We're given n points in a plane, and those set of points are s, xi, yi, such that I equals 1, 2 to n. And we're just going to assume here, just to make things easy, because we don't want to have segments that are null, or segments that are a little bit different because they're discontinuous. But we're going to assume that no two have the same x coordinate. This is just a matter of convenience. And no two have the same y coordinate. And then finally, no 3 in a line. Okay. Because we want to be able to look at pairs of points and find these segments. And it just gets kind of inconvenient. You have to do special cases if 3 of them are on a line. And so the convex hull itself is the smallest polygon containing all points in S, and we're going to call that CH of S, okay, convex hull of S. As smallest convex polygon. Thank you. And so, just as an example on the board, when you have something like this, you're going to have your convex hull being that. This one is inside of it. These 2 points are inside of it, and all of the other ones from the hull. And so we might have P, Q, R, S, T, U, and V and X are inside of the hull. They're not part of the specification of CH of S, which I haven't quite told you how we're going to specify that. But the way we're going to specify that is simply by representing it as a sequence of points that are on the boundary, on the hull, in clockwise order. And you can think of this as being a doubly linked list in terms of the data structure that you'd use if you coded this up. So in this case, it would be P to Q to R to S. You're going to start with P in this case. It's a doubly linked list. So you could conceivably start with anything. But that's the representation of the convex hull. Right? And we're going to use clockwise just because we want to be clear as to what order we're enumerating these points is going to become important when we do the divide and conquer algorithm. So let's say that we didn't care about divide and conquer just for the heck of it. And I gave you a bunch of points over here. Can you think of a simple, forget efficiency, for just a couple of minutes. Can you think of a simple algorithm that would generate the segments of the convex hull? For example, I do not want to generate this segment Vx. If I think of a segment as being something that is defined by 2 points, then I don't want to generate the segment Vx, because clearly the segment is not part of the convex hull. But whereas the segment PQ, QR, RS, etc., they're all part of the convex hull, right? So what is the obvious brute force algorithm, forgetting efficiency, that given this set of points will generate one by one the segments of the convex hull? Anybody? Did you have your hand up? No? Go ahead. Yeah. Draw the line and check how many lines it intersects with. Is there? I think you draw the line. That's good, right? Well, but you want to do a little bit more. Yeah. Go ahead. Yeah.
For every pair of points, you make a half plate and see whether it contains all of the other points, and keep doing that until you get all the.
So that's good. That's good. All right. So the first person who breaks the ice here always gets a frisbee. Sorry, man. At least I only hit the lecturer, right? No liability considerations here. Okay, now I'm getting scared. Right. So I think there's a certain amount of, when I throw this, am I going to choke or not, right? But it's going to get harder when one of you guys at the back answers the question. So you're exactly right, and you draw a line, and then you just look at it, and you look at the half plane, and if all the points are to one side, it is a segment of the convex hull. If they're not, it's not a segment. Beautiful, right? Are we done? Can we go enjoy the good weather outside? Right? No, we got a ways to go here, right? So this is not a segment, whereas this one, let me draw that. I should draw these in dotted way. This is not a segment. This is not a segment. This is a segment. And I violated my rule of these three not being in a straight line, so I'll move this over here. And then that's a segment, and so on and so forth. Okay? Right? I'm sorry? Oh, you're right. That's a good point. That's an excellent point. So what happened here was, when I moved that out, you're exactly right. Thank you. This is good. So when I moved this out here, what happened was, and I drew this, well, this one here, my convex hull changed. The problem specification changed on me. It was my fault. But then what would happen, of course, is as I moved this, that would become the segment that was part of the convex hull. Okay? So sorry to confuse people, but what we have here in terms of an algorithm, if I leave the points the same, works perfectly well. Right? So let me just leave the points the same and just quickly recap, which is I'm going to take a pair of points and I'm going to draw, and let me just draw this in a dotted fashion first, and I'm going to say that's the segment. Now I'm going to take a look at that line and say this breaks up the plane into two half planes. Are all the points on one side? And if the answer is yes, I'm going to go ahead and boom, say that is a segment of my convex hull. If the answer is no, like in this case, I'm going to drop that segment. Okay? So now let's talk about complexity. Let's say that there are n points here. And how many segments do I have? I have order n squared, theta n squared segments. And what is the complexity of the test? What is the complexity of the test that's associated with, once I've drawn the segments, deciding whether the segment is going to be a tangent, which is part of the convex hull or not? What is the complexity? ON. Exactly right. So ON test complexity. And so we got overall theta n cubed complexity. Okay? So it makes sense to do divide and conquer if you can do better than this, because this is a really simple algorithm. Right? The good news is we will be able to do better than that. And now that we have a particular algorithm, I'm not quite ready to show you that yet. Now that we have a particular algorithm, we can think about how we can improve things. And of course, we're going to use divide and conquer. So let's go ahead and do that. And so generally with divide and conquer, as I mentioned before, in most cases, the division is pretty straightforward. And that's the case here as well. All the fun is going to be in the merge step, right? So what we're going to do, as you can imagine, is we're going to take these points and we're going to break them up, right? And the way we're going to break them up is by dividing them into half planes. We're going to just draw a line, and we're going to say everything to the left of the line is one subproblem. Everything to the right of the line is another subproblem. Go off and find the convex hull for each of the subproblems. If you have 2 points, you're done, obviously. It's trivial. And at some point, you can say, I'm just going to deal with brute force. We can go down to order n cubed. If n is small, I can just apply that algorithm. So it doesn't even have to be the base case of n equals 1 or n equals 2. That's a perfectly fine thing to do. But you can certainly go with n equals 10, as I mentioned before, and run this brute force algorithm. And so at that point, you know that you can get down to small enough size subproblems for which you can find the convex hull efficiently. And then you got these two convex hulls, right, which are clearly on, well, two different half planes, because that's the way you defined them. And now you got to merge them, right? And that's where all the fun is, okay? So let's just write this out again. We're going to sort the points by x coordinates. And we're going to do this once and for all. We don't have to keep sorting here, because we're just going to be partitioning based on x coordinates. And we can keep splitting based on x coordinates, because we want to generate these half planes, right? So we can do this once and for all. And for the input set S, we're going to divide into the left half A and right half B by the x coordinates. And then we're going to compute CH of A and CH of B recursively. And then we're going to combine. So the only difference here from what we had before is the specification of the division. It looked pretty generic. It's similar to the paradigm that I wrote before, but I've specified exactly how I'm going to break this up. All right? So let's start with the merge operation. And we're going to spend most of our time speccing that. And again, there's many ways you could do the merge, and we want the most efficient way. That's obviously going to determine complexity. So big question, how to merge. Right. So what I have here, if I look at the merge step, is I've created my two subproblems corresponding to these two half planes. And what I have here is, let's say I've generated at this point a convex hull associated with each of these subproblems. Okay, so what I have here is A1, A2. I'm going to go clockwise to specify the convex hull. And the other thing that I'm going to do is, in the subproblem case, my starting point is going to be, for the left subproblem, the coordinate that is that has the highest x value. Okay, so that's A1 in this case, the highest x value going over, x is increasing to the right. And for the right half of the problem, it's going to be the coordinate that has the lowest x value. And I'm going to go clockwise in both of these cases. So when you see an ordering here associated with the subscripts for these points, start with A1 or B1, and then go clockwise. And that's how we number this, right? So just notational, nothing profound here. So I got these two convex hulls, these sub-hulls, if you will. And what I need to do now is merge them together. And you can obviously look at this, and it's kind of obvious, what the overall convex hull is, right? But the key thing is, I'm going to have to look at each of the pairs of points that are associated with this and that, and try to generate the tangents, the new tangents that are not part of the sub-hulls, but they're part of the overall hull, right? And so in this case, you can imagine an algorithm that is going to kind of do what this brute force algorithm does, except that it's looking at a point from here and a point from here, right? So you can imagine that I'm going to do a pairwise generation of segments, and then I'm going to check to see whether these segments are actually tangents, they're part of the overall convex hull or not, okay? So what I would do here is I'd look at this, and is that going to be part of the overall hull? No. And precisely why not? Someone tell me why this segment, A1, B1, is not part of the overall hull? Yeah, go ahead. Exactly right. That's exactly right. So here you go. So that's not part of it. Now, if I look at this, well, same reason, that's not part of it. In this case, and this is a fairly obvious example, I'm going to do something that's slightly less obvious in case you get your hopes up that we have this trivial algorithm. Okay, this is looking good, right? That's supposed to be a straight line, by the way. Okay, so A4, B2, I mean, that's looking good, right? Because all the points are on one side. So A4, B2 is our upper tangent, right? So our upper tangent is something that we're going to define as, if I look at each of these things, I'm going to say they have a yij. Okay, what is yij? Yij is the y coordinate of this of the segment that I'm looking at, the ij segment. So this yij is for ai and bj. So what I have here is y42 out here, and this is for the upper tangent. Yij is going to be maximum, right? Because that's essentially something which would ensure me that there are no points higher than that, right? So if I go up all the way and I find this that has the maximum Yij, that is going to be my upper tangent, because only for that will I have no points ahead of that, okay? So Yij is upper tangent. This is going to be maximum. And I'm not going to write this down, but it makes sense that the lower tangent is going to have the lowest Yij. All right? Are we all good here? Yeah, question?
So I'm just wondering, I couldn't hear what you said, why you moved out A1, B1.
Okay, so good. The reason we moved out A1, B1 is because if I just drew A1, B1 like this, and I'm extrapolating this is again supposed to be a straight line, then you clearly see that there are points on either side of the A1, B1 segment when you look at the overall problem, correct? You see that on A1, B1, B2 is on this side, B3 is on this side. If I just extend this line all the way to infinity in both directions, and that violates the requirement that this segment be part of the overall hull, okay? That makes sense? Good. So everybody with me? So clearly, there is a trivial merge algorithm here, and the trivial merge algorithm is to look at every pair of points, every A-B pair, right? Every AI-BJ pair. And so what is the complexity of doing that? if I have n total points, the complexity would be n squared, right? Because maybe I'd have half here and half there. Ignore constants, and you could say, well, it's going to be n squared divided by 4, but that's theta n squared, right? So there's an obvious merge algorithm that is theta n squared, looking at all pairs of points. And when I mean all pairs of points, I mean like an A and a B, because I want to pick a pair where I go left of that dividing line and then right of the dividing line. But either way, it's theta n squared. Okay? So now you look at that and you go, can I do better? What if I just went for the highest A point and the highest B point, and no, that's it, I'm done. Constant time. Wouldn't that be wonderful? Yeah, wonderful, but incorrect. Okay, right? So what is an example? And so this is something that I spent a little bit of time last night concocting. So I'm like you guys too. I do my problem set the night before. Well, don't do as I do. Do as I say, right? But I've done this before, so that's the difference. But this particular example is new. So what I have here is I'm going to show you why there's not a trivial algorithm, okay, that I got to get these angles right. You can't just pick the highest points and keep going, right? And then that would be constant time. So that's my A over here, and let's assume that I have my dividing line like that. And then what I'm going to do here, and I hope I get this right, is I'm going to have something like this, like that, and then I'm going to have B1 here clockwise, so B2, B3, and B4. Okay? So as you can see here, if I look at A4, a little adjustment necessary. Okay? So if I look at that, A4 to B1 versus, just eyeball it, A3 to B1, right? Is A4 to B1 going to be the upper tangent? No, right? So now A3 is lower than A4. You guys see that? And B1 is lower than B2, right? So it's clear that if I just took A4 to B2, that it would not be an upper tangent. Everybody see that? Yep. All right. Good. So we can't have a constant time algorithm. We have the theta n squared in the bag, right? So is there something, maybe theta n? How would we do this merge and find the upper tangent by being a little smarter about searching for pairs of points that will give us this maximum Yij, right? The goal here is simple. It's at some level, if you looked at the brute force, I would generate each of these things. I'd find the Yij intercepts associated with this line, and I'd just pick the maximum, right? And the constant time algorithm doesn't work. The theta n squared algorithm definitely works, but we don't like it. So there has to be something in between, right? So any ideas? Yeah, back there. Yeah. No, you're just you're maximizing the Yij. So for once you have the segment, so the question was, isn't the obvious merge algorithm theta n cubed, right? And my answer is no, because the theta n extra factor came from the fact that you had to check every endpoint to see on which side of the plane it was. Whereas here, what I'm doing is I got this one line here that is basically y equals 0, if you like, right? Or y equals some, x equals 0, or x equals some value. And I just need to, once I have the equation for the line associated with A4B1 or A4B2, I just have to find the intercept of it, which is constant time, right? And then once I find the intercept of it, I just maximize that intercept to get my Yij, so I'm good. Okay? So it's only theta n square. Right? Good question. So this is actually quite very, very clever. This particular algorithm is called the two-finger algorithm. And I do have multiple fingers, but it's going to work out better if I borrow Eric's finger. And we're going to demonstrate to you the two-finger algorithm for merging these two convex hulls. And then we'll talk about the complexity of it. Okay? And my innovation, again, last night, was to turn this from a two-finger algorithm. Not only did I have the bright idea of using Eric, I decided it was going to become the two-finger and string algorithm. Okay? So this is wild. This is my contribution to 046 lore. Come on. Right? So the way the two-finger algorithm works, and this pseudocode should be incomprehensible. Okay? If you just look at it and you go, what? Right? But this demo is going to clear everything up. Right? So here's what you do. So now we're going to do a demo of the merge algorithm that is a cleverer merge algorithm than the one that uses order n square time. And it's correct. It's going to get you the correct upper tangent. And what we are starting at here is with Eric's left finger on A1, which is defined to be the point that's closest to the vertical line that you see here, the one that has the highest x coordinate. And my finger is on B1, which is the point that has the smallest x coordinate on the right-hand side subhull. And what we do is we compute for the segment A1, B1, we compute Yij, in this case Y11, which is the intercept on the vertical line that you see here that Eric just marked with a red dot. And you can look at the pseudocode over on to my right if I face the board. And what happens now is I'm going to move clockwise, and I'm going to go from B1 to B4. And what happened here? Did the Yij increase or decrease? Well, as you can see, it decreased. And so I'm going to go back to B1. And we're not quite done with this step here. Eric's going to go counterclockwise over to A4. And we're going to check again. Yeah, keep the string taut. Check again whether Yij increased or decreased. And as is clear from here, Yij increased. So now we move to this point. And as of this moment, we think that A4B1 has the highest Yij. But we have a while loop. We're going to have to continue with this while loop. And now what happens is I'm going to go from B1 clockwise again to B4. And when this happens, did Yij increase or decrease? Well, it decreased. So I'm going to go back to B1. And Eric now is going to go counterclockwise to A3. And as you can see, Y31 increased a little bit. So we're going to now stop this iteration of the algorithm. And we're at A3B1, which we think at this point is our upper tangent. But let's check that. Start over again on my side, B1 to B4. What happened? Well, Yij decreased. So I'm going to go back to B1. And then Eric's going to try, he's going counterclockwise. He's going to go A3 to A2. And, well, big decrease in Yij. Now Eric goes back to A3. At this point, we've tried both moves, my clockwise move and Eric's counterclockwise move. My move from B1 to B4 and Eric's move from A3 to A2. So we've converged. We're out of the while loop. A3B1 for this example is our upper tangent. All right? You can have your finger back, Eric. So the reason this works is because we have a convex hull here and a convex hull here. We're starting with the points that are closest to each other in terms of A1 being the closest to this vertical line, B1 being the closest to this vertical line. And we're moving upward in both directions because I went clockwise and Eric went counterclockwise. And that's the intuition of why this algorithm works. We're not going to do a formal proof of this algorithm, but the monotonicity property corresponding to the convexity of this subhull and the convexity of this subhull essentially can give you a formal proof of correctness of this algorithm. But as I said, we won't cover that in 046. So all that remains now is to look at our pseudocode, which matches the execution that you just saw, and talk about the complexity of the pseudocode. What is the complexity of this algorithm? It's order n, right? So what has happened here, if you look at this while loop, is that while I have two counters, I am essentially looking at two operations per loop, and either one of those counters is guaranteed to increment through the loop. And so since I have, in this case, p points, in one case, p plus q equals n. So let's say I had p points here, and I have q points here, and I got p plus q, let's say, equals n. Then I got a theta n merge, simply because I'm going to be running through and incrementing. As long as I'm in the loop, I'm going to be incrementing at either the I or the j, and the maximum that can go to are p and q before I bounce out of the loop or before I rotate around. And so that's why this is theta n. And so you put it all together in terms of what the merge corresponds to in terms of complexity, and put that together with the overall divide and conquer. We have a case where this is looking like a recurrence that you've seen many a time. T of n, I've broken it up into two subproblems. So I have two, and I could certainly choose this L over here, that's my line, L, to be such that I have a good partition between the two sets of points. Right? Now if I choose L to be all the way on the right-hand side, then I have this large subproblem, makes no sense whatsoever. So what I can do, there's nothing that's stopping me when I've sorted these points by the x-coordinates to do the division such that there's exactly the same number, assuming an even number of points n, exactly the same number on the left-hand side or the right-hand side. But I can get that right roughly, certainly within 1, very easily. So that's where the n over 2 comes from. Okay. In the next problem that we'll look at, the median finding problem, we'll find that trying to get the subproblems to be of roughly equal size is actually a little difficult. Okay. But I want to point out that in this particular case, it's easy to get subproblems that are half the size because you've done the sorting, and then you just choose the line, the vertical line, such that you got a bunch of points that are on either side. And then in terms of the merge operation, we have 2t n over 2 plus theta n. People recognize this recurrence? It's the old merge sort recurrence. So we did all of this in, well, it's not merge sort. Clearly, the algorithm is not merge sort. But we got the same recurrence. And so this is theta n log n. So a lot better than theta n cubed. Okay? And there's no convex hull algorithm that's, in the general case, better than this. Even the gift wrapping algorithm that I mentioned to you, with the right data structures, it gets down to that in terms of theta n log n, but no better. Okay? So good. That's pretty much what I had here. Again, like I said, happy to answer questions about the correctness of this loop algorithm for merge later. Any other questions associated with this? Yeah, back there. No, you can't, because I mean the n log n for the pre-sorting. I mean there's another theta n log n for the sorting at the top level, and we didn't actually use that, right? So the question was, can we do better if the input was pre-sorted? And I actually did not even use the complexity of the sort We just matched it in this case, right? So theta n log n. And you can imagine maybe that you could do a theta n sort if these points were small enough and you rounded them up, then you could use a bucket sort or a counting sort and lower that, right? So this theta n log n is kind of fundamental to the divide and conquer algorithm. It's the only way you can improve that is by making a merge process that's even faster, okay? And we obviously tried to cook up a theta 1 merge process, but that didn't work out, okay? First, if you assume certain things about the input, you absolutely, right? So one thing you'll discover in algorithms and in 6046 as well is that we're never satisfied. Okay, so I just said, oh, you can't do better than theta n log n, but that's in the general case, and I think I mentioned that. You're on the right track. If the input is pre-sorted and you can take that away, well, it doesn't help in that particular instance if you have general settings. But if you, the two-dimensional case, if you, the hull, all the segments are have a certain characteristic, not quite planar, but something that's a little more stringent than that, you can imagine that you can do improvements. I don't know of any compelling special case input for convex hull for which you can do better than theta n log n. But that's a fine exercise for you, which is, in what cases, given some structure on the points, can I do better than theta n log n? Right? So that's something that keeps coming up in the algorithm literature, if you can use that. Okay? So, yeah, back there, question. Great point. And you're absolutely right. And I just realized that I skipped that step. Right? Thank you so much. So the question was, how do I remove the lines? And it's actually fairly straightforward. Let's keep this up here. And we don't need this incomprehensible pseudocode, right? So let's erase that. And thank you for asking that question. So it's a little simple cut and paste approach where, let's say that I find the upper tangent AI bj, okay, and I find the lower tangent, let's call it AK bm, and in this particular instance, what do I have? I have A1, A2, A3, A4 as being one of my subhulls, and then I have B1, B2, B3, B4 as the other one, right? Now, what did we determine to be the upper tangent? Was it A3B1, right? A3B1. So A3B1 was my upper tangent, and I guess it was A1B4. A1B4 was my lower tangent. So the big question is, now that I have found these two, how do I generate the correct representation of the overall convex hull? All right, and so it turns out that you have to do this. And the complexity of this is important as well. And you need to do what's called a cut and paste that's associated with this, where we're going to just look at this and that, right? So we're going to have these two things, and we're going to generate a list of points. Now, clearly, A4 is not going to be part of that, right? A4 is not going to be part of the overall hull. What is it that we want? We want something like A1, A2, A3, B1, B2, B3, B4, right? But there's a point that we have to discard here. Agreed? And so the way we do this is very mechanical. That's the good news here. I mean, you don't have to look at it pictorially. I just made that up, eyeballing it. Clearly, the computer doesn't have eyeballs, right? And so what we're going to do is we're going to say the first link, in general, the first link is AI to BJ, because that's my upper tangent, okay? And in this case, it's going to be A3B1, okay? And then I'm going to go down the B list till I see till you see BM, which is the lower tangent. You're on the B list, so you're looking for the lower tangent point. And then you're going to jump till you see BM. You link it to AK. Okay? You link it to AK and continue till you return to AI. Right? And then you have your circular list. Okay? So what you see here is you have A3 here. So I'm going to go ahead and write out the execution of what I just wrote here. So I have A3, and I'm going to go jump over to B1. So I'm going to write down B1. Then I'm going to walk along the B's until I get to B4. In this case, I'm going to include all of the B's. So I got B1, B2, B3, B4. And then I'm going to jump from B4 to A1 because that's part of my lower tangent. And I got A1 here, A2, and then I'm back to A3, which is great because then I'm done. Okay? And so exactly what I said happened, thank goodness, which is we dropped A4, but we kept all the other points. All right? So answer your question? Good. What is the complexity of cut and paste? It's order n. I'm just walking through these lists. So there's no hidden complexity here. Okay? Good, good. Thank you. You desperately deserve a Frisbee. In fact, you deserve 2. Right? Where are you? Could you stand up? Yeah. Right. Two colors. All right. Oh, so well, you can give it to him if you like. But so good. Thank you. So are we done? Are we done with convex hull? Okay, good. So let's go on and do median finding. Very different set of issues here. Still a divide and conquer, but a very different set of issues. The specification here is, of course, straightforward. You can think of it as, I just want a better algorithm than sorting and looking for the median at a particular position, n over 2 position. For example, let's say n is odd, and it's floor of n over 2. You can find that median, right? So it's pretty easy if you can do sorting. But we're never satisfied with using a standard algorithm if we think that we can do better than that. So the whole game here is going to be, I want to find the median, and I want to do it in better than theta n log n time. Okay? So that's what median finding is all about. We're going to use divide and conquer for this. And so in general, we're going to define, given a set of n numbers, define rank of x as the numbers in the set that are greater than, I'm sorry, less than or equal to x. I mean, you could have defined it differently. We're going to go with less than or equal to. So in general, the rank, of course, is something that you could be used very easily to find the median. So if you want to find the element of rank n plus 1 divided by 2 floor, that's what we call the lower median. And n plus 1 divided by 2 ceiling is the upper median. And they may be the same if n is odd. But that's what we want. So you can think of it as not median finding, but finding elements with a certain rank. And we want to do this in linear time. Okay? So we got to apply divide and conquer here. And as always, the template can be instantiated, and the devil is in the details of either division or merge. And we had most of our fun with convex hull on the merge operation. It turns out most of the fun here with respect to median finding is in the divide. Okay, so what I want is the definition of a select routine that takes a set of numbers S, and this is the rank. So I want a rank I, and that I might be n over 2, floor of n plus 1 over 2, whatever. And so what does the divide and conquer look like? Well, the first thing you need to do is divide. And as of now, we're just going to say, we're going to pick some element, x, belonging to S. And this choice is going to be crucial. But at this point, I'm not ready to specify this choice yet. Okay? So we're going to have to do this cleverly. And then what we're going to do is we're going to compute k, which is the rank of x, and generate two subarrays such that I want to find the 5th highest element, I want to find the median element, I want to find the 10th highest element. So I have to keep track of what happens in the subproblems, because the subproblems are going to determine, depending on how many elements are inside those subproblems, which I can only determine after I've solved those subproblems. I'm going to have to collect that information and put it together in the merge operation. So if I want to find the 10th highest element, and I've broken it up relatively arbitrarily, it's quite possible that the 10th highest element is going to be discovered in the left one or the right one, and I have to show that it's the 10th highest. And it might be that there's 4 elements in the left and 5 on the right that are let's see, if I define the rank as less than or equal to x, there's 4 on the left and 5 on the right that are smaller, and that's why this is the 10th highest element. And that's essentially what we have to look at. So B and C are going to correspond to the subarrays that you can clearly eliminate one of them. You can count the number of elements in B, count the number of elements in C, and you can eliminate one of them in this recursion as you're discovering this element with the correct rank, in this case I. So let me write the rest of this out and make sure we're all on the same page. What I have here pictorially is I've generated B here and C. So this is all of B and that's all of C. I have k minus 1 elements here in B. And let's say I have n minus k elements in C. And I'm going to essentially take, once I've selected a particular element, I'm going to look at all of the elements that are less than it and put it into the array B. I'm going to look at all the elements that are greater than it. Let's assume all elements are unique. I'm going to put all of them into C. And I'm going to recur on B and C. That's, those two are my subproblems. But what I have to do is, once I recur and I've discovered the ranks of the subproblems, I have to put them together. So what I have here is, if k equals I, if I've computed the rank, and I realize that if k equals I should say, if k equals I, then I'm going to just return x. I'm done at this point. I got lucky. I picked an element x, and it magically ended up having the correct rank. Okay, not always going to happen. And so in other case, if k is greater than I, then I'm going to return select bi. So what I've done here is, if k is greater than I, then I'm going to say, oh, so now I'm going to have to find the element in B. I know that it's going to be in B because k is greater than I, and I got to find the exact position depending on what I is over here. But it's going to be somewhere between 1 and k minus 1. Okay, and then the last case is if k is less than I, then this is a little more tricky. I'm going to return C of I minus k. Okay, so what happens here is that my k is that the rank for the x that I've looked at over here is less than I. So I'm going to look, I know that I'm going to find this element that I'm looking for in C. But if I just look at C, I don't want to look at C and look for an element of rank I within C, right? That doesn't make sense because I'm looking for an element of rank I in the overall array that was given to me. So I have to subtract out the k elements that correspond to X and all of the k minus 1 elements that are in B to go figure out exactly what position or rank I'm looking for in the subarray corresponding to C. Okay? So people buy that? So that's just a small little thing that you have to keep in mind as you do this. Right, so that's pretty straightforward, looking pretty good. And you say, well, am I done here? And as you can imagine, the answer is no, because we haven't specified this value. Now, can someone tell me, at least from an efficiency standpoint, what might happen? What we're looking for here, as you can imagine, we want to improve on theta n log n. And so you could say, well, I'm happy with theta n. A theta n complexity algorithm is better than a theta n log n complexity algorithm, which is kind of in the bag because we know how to sort and we know how to index. Right? So we want a theta n algorithm. Now, if you take this and if I just picked, let's say, the biggest element, or I kept picking x to be n or n minus 1, or just pick a constant value. I picked x to be in the middle, right? I pick the index. I can always pick an element based on its index. I can always go for the middle one, right? So what is the worst case complexity of this algorithm? For if I don't specify, or I give you this arbitrary selection corresponding to x belonging to S, what is the worst case complexity of this algorithm? Right? Yeah, go ahead. N squared. Why is that? Yeah. Exactly right. That's exactly right. So what happens here is that you're doing a bunch of work here with this theta n work, right? Right here, this is theta n work. Okay. So given that you're doing theta n work here, you have to be really careful as to how you pick the x element. So what might happen is that you end up picking the x over here, and given the particular rank you're looking for, you have to now, you're left with a large array that has n minus 1 elements in the worst case. You started with n, you did not go to n over 2 and n over 2, which is what divide and conquer is all about, or even n over b, okay? You went to n minus 1, and then you go to n minus 2, and then you go to n minus 3, because you're constantly picking, this is worst case analysis, you're constantly picking these subarrays to be extremely unbalanced, right? So when the subarrays are extremely unbalanced, you end up doing theta n work in each level of the recursion. And those theta n's, because you're going down all the way from n to 1, are going to be theta n squared when you keep doing that, okay? So, good. Thanks for that analysis. And so this is theta n squared if you have a bad selection. Okay. So we will talk about randomized algorithms, but the problem with randomized algorithms is that the analysis will be given a probability distribution, and it'll be expected time. What we want here is a deterministic algorithm that is guaranteed to run in worst case theta n. Right? So we want a deterministic way of picking x belonging to S such that all of this works out and when we get our recurrence and we solve it, somehow magically we're getting fairly balanced partitions, fairly balanced subproblems, in the sense that it's not n minus 1 and 1. It's something like, it could even be n over 10 and 9n over 10. But as long as you guarantee that, you are shrinking things down geometrically, and the asymptotics is going to work out. Okay? But that's the determinism is what we need. And so we're going to pick x cleverly. All right. And we don't want the rank x to be extreme. So this is not the only way you could do it, but this is really very clever, this deterministic way. And you're going to see some arbitrary constants here, and we'll talk about them once I've described it. But what we're going to do is we're going to arrange S into columns of size 5. Right? We're going to take this single array and we're going to make it a two-dimensional array where the number of rows is 5 and the number of columns that you have is n over 5, ceiling in this case. And then we're going to sort each column, big elements on top, and we're going to do this in linear time. And you might say, how did that happen? Well, there's only 5 elements, so it's linear, right? You could do whatever you wanted. You could do n raised to 4, but it's 5 raised to 4, and it's constants. Don't you love theory? So then we're going to find what we're going to call the median of medians. So I'm going to explain this. This works for arbitrary rank, but it's a little easier to focus in on the median to just explain the particular example, because as you can see, there's some intricacy here associated with the breakup. And so here we go. I'm going to draw out a picture, and we're going to try and argue that this deterministic strategy that I'll specify gives you fairly balanced partitions in all cases. Okay? So what we see here is, we see pictorially, you see columns of length 5. Right? Each of these dots corresponds to a number. This one-dimensional array got turned into a two-dimensional array. Right? So I got 4 full columns, and it's certainly possible, given n, that my 5th column is not full, right? So that's certainly possible. So that's why I have that up here. So what I have here is I'm going to lay them out this way, and I'm going to look at that. I'm going to look at the middle elements of each of these n over 5 columns. Right? That's exactly what I'm going to look at. Now, if I look at what I want over here is this x. If I want to find, I'm going to find the median of medians. So this is x. Now, it is true, of course, that these columns, I'm just putting that up here, imagining that that's x. That's not guaranteed to be x, because the columns themselves aren't, well, each of these columns is sorted. And what I'm going to have to guarantee, of course, is that when I go find this median of medians, is that it ends up being something that gives me balanced partitions. Right? So let me say a little bit more before I explain what's going on. Each of these columns is sorted, and S is arranged into columns of size 5, like I just said here. These are the medians. Okay. If I look at if I look at determining the medians, and I say that once I've determined this x, which I've discovered that it's the median, then this is right there in the middle. there's going to be a bunch of columns to the left of it, bunch of elements to the left of it, and a bunch of elements to the right of it. And in this case, I have 5 columns. I could have had more. It happens to be the third one. So the idea is that once I find this median of medians, which corresponds to this x number, I can say that all of the columns, these are all correspond to columns that have their median element greater than x. These correspond to columns that have their median element less than x. Okay? So what I have here in this picture is that these elements here are going to be greater than x. Okay? And these elements here are going to be less than x, right? So let me be clear. What's happened here is we've not only sorted all of the columns such that you have larger elements up here. Each of these 5 columns has been sorted that way. On top of that, I've discovered the particular column that corresponds to the median of medians, and this is my x over here. And it may be the case that these columns aren't sorted. This one may be larger than that, or vice versa, same thing over there. I have no idea. But it's guaranteed that once I find this median, that I do know all of the columns that have elements that in this position that are less than this x, and I know columns that in this position have elements that are greater than x. Okay? Yeah.
Should the 2 elements below x also be included in the group of elements less than x?
You're exactly right. I would have probably been able to get the same asymptotic complexity if I dropped those because I had a constant number, but you're absolutely exactly right. Right? So the point that the question was, I just redrew it. These 2 are clearly less than x as well because they're part of the sorting. Right? That's essentially what I have here. Now my goal here, and you can kind of see from here as to where we're headed. Right? What I've done here by this process of sorting each column and finding the median of medians is that I've found this median of medians such that there's a bunch of columns on the left, and roughly half of those elements in those columns are less than x, and then there are a bunch of columns on the right, and roughly half of those columns have elements that are greater than x. So what I now have to do is to do a little bit of math to show you exactly what the recurrence is, and let me do that over here. So that's the last thing that we have to do. I probably won't solve the recurrence, but that can wait till tomorrow. The recurrence will be something that's not particularly difficult to solve. So I want to now make a more quantitative argument with the variable being n as to how many elements are guaranteed to be greater than x. And essentially what I'm saying, which is I'm writing out what I have on that picture there, half of the n over 5 groups contribute at least 3 elements greater than x, except for one group with possibly less than 5 elements, which is the one that I have all the way to the right, and one group that contains x. So for all the other columns, I'm going to get 3 elements that are greater than x. And so if you write that out, this says there are at least 3 n over 10, because I have half of all of those groups, minus 2. And I'm not counting perfectly accurately here, but I have an at least, so this should all be fine. 3n over 10, 3 times n over 10 minus 2 elements are strictly greater than x, right? And that comes from that picture. I'm going to be able to say the same thing for less than x as well. I can't count the 1. Depending on how things go, maybe I could have played around and subtracted a 1 instead of a 2 in the latter case, but I'm just being conservative here. It is clear that I'm going to have a bunch of columns that are full columns that have going to be contributing 3 elements that are greater than x, and in this case I have, well, 2 of them here for the less than x, and I got 1 for the greater than x. Right? So that's all that I'm saying over here with respect to the balance of the partitions. And it turns out that's enough. It turns out all I have to do with this observation is to go off and write the recurrence, and we're going to get an efficient algorithm. Yeah?
Should it not be like greater than or equal to? Because there's nothing
No, there's nothing that's equal.
it's all unique.
Yeah. Yeah, I assume that, so convenience, yeah, there's always a little bit of convenience thrown in here. We will assume that that the array has unique elements. So there's nothing that's x, okay? Good. So the recurrence, once you do that, is T of n equals, we're going to just say it's order 1 for n less than or equal to 140. Where did that come from? Well, I like 140. It's just a large number. It came from the fact that you're going to see 10 minus 3, which is 7, and then you want to multiply that by 2. So some reasonably large number, we're going to go off and we're going to assume that's a constant. So you could sort those 140 numbers and find the median or whatever rank. It's all constant time once you get down to the base case. Right? So you just want it to be large enough such that you can break it up and you have something interesting going on with respect to the number of columns. Right? So don't worry too much about that number. The key thing here is the recurrence. Right? And this is what we have to spend the rest of our time on. And I'll just write this out and explain where these numbers came from. All right, so that's our recurrence. If for n less than or equal to 140, and else you're going to do this. So what is going on here? What are all of these components corresponding to this recurrence? Really quickly, this is simply something that says I'm finding the median of medians. I'm finding some element that has a certain rank. So this median of medians is going to be running on n over 5 columns. So I'm going to, there are n over 5 columns here, and I'm going to be calling this algorithm recursively the median finding algorithm to do that, finding the median of medians. Okay. This thing over here is I'm going to be discarding at least, regardless of what I do, because I have these two statements here, I take the overall n, and I'm going to discard in my paradigm over here. I'm either going to go with B or I'm either going to go with C, depending on what I'm looking for. And given that B and C are not completely unbalanced, I'm going to be discarding 3n over 10 minus 6 elements, which simply corresponds to me ignoring the ceiling here and multiplying the 3 out. So that's 3n over 10 minus 6. So then I have 7n over 10 plus 6. That's the maximum size partition that I'm going to recur on. It's only going to be exactly one of them, as you can see from that. It's either else. It's not recurring on both of them. It's recurring on one of them. So that's where the 7n over 10 plus 6 comes from. And then you ask, where does this theta n come from? Well, the theta n comes from the fact that I do have to do some sorting. It's constant time sorting for every column, okay, because there's only 5 elements, so I'm going to do constant time sorting. But there's order n columns, right, because there's n over 5 columns. So this is the sorting of all of the columns. All right? So that's it. And I'll just leave you with, you cannot apply the master theorem for solving this particular recurrence. But if you make the observation, and you'll see this in section, if you make the observation that n over 5 plus 7n over 10 is actually less than n, right? So that you get 0.2n here and 0.7n there. That's actually less than n. This thing runs in linear time, and you'll see that in section tomorrow. So this whole thing is theta n time. See you next time.